Okay. All right. So I want to thank the organizers and the review committee for accepting our paper. It's a joint work with Ravi Bansal at Duke. The title of the paper is Risk Preferences and the Macro Announcement Premium. I want to start with the empirical fact of macro announcement premium. Empirically, a large fraction of equity premium is realized on a small number of trading days with significant macroeconomic announcement. In the period from 1961 to 2014, for example, there's on average 252 trading days per year. The average equity premium in this period is 6.19% per year. Out of the 252 trading days, 30 days of them has significant macro announcement, but it is that 30 days that accounts for 3.36% of the equity premium, which is to say that 30 days of a year, which is a small fraction of the total number of trading days, accounts for almost 60% of the entire equity premium. Most of these macroeconomic announcements that we document come in the later sample period from 1997 to 2014. In this period, again, there's total number of 252 trading days. The average equity premium is 7.44%. There's more announcement premium. So there are 50 days per year on average has a significant macroeconomic announcement. But that 50 days accounts for 24% of the equity premium, virtually 100% of the entire equity premium. So the equity premium on the rest of the trading days is actually slightly negative. Perhaps one of the well-known example of a macroeconomic announcement premium is the FOMC announcement as documented by Luca and Moyank. Most of the FOMC announcement premium is realized in several hours leading to the announcement. So this is what they call the FOMC announcement drift. The premium for other announcements, however, are realized upon and after announcements. There's no macroeconomic announcement drift, in other words, for other macroeconomic announcements. So in this figure, we plot the average market return, hourly market return around macroeconomic announcements. The top panel is for FOMC announcement. The bottom panel is for announcement return for non-FOMC announcements, which include unemployment, non-farm payroll, producers' price index, and GDP announcement. The blue column represents the hourly return during the hour before and including the announcement. It is clear that at time zero, the FOMC announcement is virtually zero. The minuses indicate number of hours before the announcement. Then pluses indicates the number of hours after the announcement. So most of the FOMC announcement come, for example, 4 hours or 5 hours before the announcement. The average announcement in 5 hours before, for example, return is about 11 basis points. If you focus on other announcements, it's clearly most of the announcement return come right at announcement, which is the average return. The average return is about 7 to 8 basis points, and there's no macroeconomic announcement drift. So what we want to do in this paper is we want to characterize the set of preferences that's consistent with the announcement premium. Our main result says the announcement premium is positive if and only if the certainty equivalence functional is increasing in second-order stochastic dominance. So one important implication of that result says announcement premium provides an asset market-based evidence for deviations from expected utility, because as a corollary, we prove that the announcement premium on all assets is zero if and only if you have expected utility. So zero announcement premium is a defining characteristic of time-separable expected utility. The quantitatively large announcement in the data cannot be compensation for the risk aversion for the von Neumann-Morgenstern expected utility. It has to be compensation for something look like a nonlinearity of the certainty equivalence functional that's captured by models, for example, that features aversion to Nician uncertainty. Our theory is going to be consistent with the FOMC pre-announcement drift if there's informal communication from Fed officials to the public before announcement as documented by the Chesler et al. Paper. So just to illustrate the ideas, let me just start with a simple example and understand when we get announcement premium. I'm going to start with a very simple example, two-period model. The only uncertainty in this economy is at date period 1, where consumption can take two values, high or low. The only interesting thing that happens at period 0, period 0 minus, agent don't know any information. There's a representative agent economy. Agent doesn't know any information. At period 0 plus, there's announcement comes. There's a news comes. For simplicity, we're just going to assume that when news come, they're going to fully resolve the uncertainty. They're going to reveal the true state of the world, even though our general theorem doesn't require this assumption. So I want to emphasize at this point the two features of news. One is that it does not change, the arrival of news does not affect current period consumption, but it only affects the conditional distribution of future consumption. Second is that if you assume rational expectation, then the law of iterated expectation tells us that the average innovations in news has to be 0. So what we're interested in is the conditions under which the average innovations in price are not 0, and not 0 in a way that you obtain an announcement premium. So here's the asset market. At time 0, you can trade a set of irreducible securities, but asset prices cannot depend on information. At time 0 plus, when information arrives, the market opens again, and presumably at this point, the prices are going to depend on information. But the payoff does not realize until period 1, where agent consumption, payoff, and so on and so forth. Let's first take a look at an example of expected. So we're going to define the announcement premium if the strategy that purchase an asset right before the news and sell right after, it's going to give you an extra return, right? So the expected price, P pluses, expected payoff divided by the price is higher than 1. That's our definition of announcement premium. Let's first take a look at expected utility. So for expected utility, we all know that if I look at pre-announcement prices, that's going to be a marginal utility weighted payoff. If I look at post-announcement prices, that's going to be a marginal utility weighted payoff, but I don't need an expectation operator because the news fully resolves the uncertainty. It's an immediate conclusion from this derivation is that there can be no pre-announcement premium because P0 minus has to be equal to expected P0 plus by law of iterated expectation. So it turns out the converse of the above statement is also true. If you have no announcement premium on any asset, then you get recovered expected utility. So in the paper we proved that no announcement premium if and only if you have expected utility. So let's take.
Hold on, I don't understand what you're saying. Can you just have it slower there?
Okay. So I'm saying. So first of all, is it clear?
Can there ever be a risk premium?
There will be a risk premium, but the risk premium will not realize until you complete your consumption. So.
That's not true. The risk premium is realized when the return comes out.
Yes.
When the information comes out. If there's no information, there's no risk premium.
So typically when we write down models, we don't really. So typically in this model, if you look at the risk premium associated with expected utility, the risk premium realizes only in period 1.
It does not. It realizes when the return. You do not earn a risk premium if there's no news coming out.
Yes, exactly. You don't earn a risk premium unless the news come out. And in the typical models that we write down, news come out only when your consumption realizes, which is period 1.
At P plus, you must earn a risk premium. Consumption's not moving, right? So, even though there's variation, the investor doesn't care. Nothing happens. That's why. Isn't the news about consumption?
This is news about future consumption. Okay, so let me say it again.
John knows something about it. I know something about it too, turns out.
So let me say it again. The important. What is important in this setup is that when news come out, current period consumption does not move. The only thing that you have with news is that it carries news about future. And therefore, you're not going to realize any premium upon news. Let's take a look at another example where let's assume the agent has the Gilbert-Schmeidler type of expected utility.
So can I ask a clarification?
Yeah.
It seems a very strong result, the only if part.
Yeah.
And I really did not get your explanation for it.
Okay, so I'll come back to that in for 5 slides. Let's look at Gilbert-Schmeidler preference. So in this case, the agent compute their utility by taking expectations over a family of probability measures indexed by M. If I assume that the family of, so imagine in a world that the nature tries to choose the worst case probability to minimize against the agent. If I assume that the probability is constrained, is chosen subject to relative entropy constraint, then you get the Hansen-Sargent robust control model. In this case, you can explicitly solve the minimizing probability. So then I can represent the expected utility. I can get rid of the minimax operator just because I can explicitly solve the minimizing probability. And that M star is going to be a pessimistic probability measure because the nature tries to minimize against the agent. So the nature is going to distort the probability in a way that they assign higher weights in states with low utility. So of course, after announcement, you have all uncertainty is resolved. You come back to this time-separable utility. So again, post-announcement return is marginal utility weighted payoff. And I don't need the expectation operator because all uncertainty resolved at this point. Pre-announcement price is going to be marginal utility weighted payoff, but now you have this distorted probability measure. Therefore, what you arrive at is an expression that looks very much like intertemporal asset pricing equation in our consumption-based asset pricing models, where P0 minus is going to be equal to something like, we call it announcement SDF because this is price announcement returns. So the only difference between this expression and our usual consumption-based asset pricing model is that there is no intertemporal substitution consumption in here. There's only information revelation, right? Because the agent has a multiple prior uncertainty aversion preferences, you're going to get a stochastic discount factor that looks like a probability distortion. Because this is a pessimistic probability distortion, it assigns a higher weight in bad states of the world and lower weight on the good states of the world, you will get a premium if this price, the payoff, is positively correlated with the continuation utilities. It turns out this result is more general. So here's our in the paper, we have a more general setup. We have a fully dynamic model. We allow preferences to have a general representation of the following form, which is Vt. So your utility at time t, lifetime utility time t, is given by the following recursion, which is U of Ct plus beta, that I is a certainty equivalence functional that maps Vt plus 1, which is a random variable, to the reals. And if you, the key result in this paper has to do with this certainty equivalence functional. If that certainty equivalence functional is expectation operator, then you'll get back to your Bellman equation for expected utility. But that can be the recursive utility operator. You get your Epstein and Zin's preference. That can be the minimax operator. That can be the smooth ambiguity aversion operator of Kalibanov. It could be the variational preference that has been proposed by Macaroni and et al. So it almost includes all of the non-expected utilities as special, that has been studied for asset pricing as special cases. So in this general setup, we want to understand what does announcement premium say about this certainty equivalence functional? Or what does announcement say about preferences? Our main result is that let's assume non-atomic probability space. Let's assume differentiability, because we want to take partial derivatives and study asset prices. Then a positive announcement premium if and only if that certainty equivalence functional is increasing in second-order stochastic dominance. Motivated by that result, we're just going to define the class of preferences that has a certainty equivalence functional that's increasing in second-order stochastic dominance as generalized risk sensitivity. We're just going to give it a name. So this is how we want to interpret our results. The main question that we want to ask in this paper is, what do asset prices tell us about preferences, in particular announcement premium, right? So our main result is that a positive premium, announcement premium, is a characterizing property of what we call generalized risk sensitivity. And if you have no announcement on any asset, this comes back to Willie's question. If you have expected utility, you definitely have no announcement return, as I said. But if you have no announcement premium on any possible asset that you can construct, you recover expected utility. So I like to think of this as a kind of reviews preference approach, because think about our typical consumption-based asset pricing model. We start from assumptions on preferences and technologies, and we want to think about asset pricing implications of those preferences, right? Our approach is kind of more similar to the approach taken by the decision theoretic literature, where people start from axioms on choices, and people want to ask, what is the utility representation for a preference that satisfies a certain set of axioms, right? So our approach, we didn't start from choice behavior, individual choice behavior. We started from asset prices, right? We want to ask a particular phenomenon on the asset market, in particular announcement premium. What does it tell us about preferences, right? So we want to go from asset prices to recover preferences. And what is the intuition? How do we recover preferences from asset prices? Well, asset prices are priced using marginal utilities. So a particular asset pricing phenomenon put restrictions on your marginal utilities. Marginal utility is basically a derivative of the utility function. If I have enough information on asset prices, I can integrate the derivatives and recover the underlying preference. And I can say something about the underlying preference. It turns out that the announcement premium is informative about, it turns out that the premium associated with resolution of uncertainty. That's what announcement premium is, because announcement resolves uncertainty about future, right? The premium associated with resolution of uncertainty is informative about how agents aggregate uncertainty across states of the world to compute certainty equivalence. Just to give you some intuition, why does announcement premium tell us about, is equivalent to what we call generalized risk sensitivity? So when you compute asset prices, you basically take marginal utility weighted payoffs, right? When you compute marginal utility, you're going to do chain rule, which is you first compute marginal, the derivative of certainty equivalence with respect to continuation utility, and then you take derivative of continuation utility with respect to consumption in the future. If you assume that news fully revealed the true states of the world, the second piece that comes from the chain rule is just going to be the post-announcement return. Therefore, you have an expression that looks like the partial derivatives of the certainty equivalence functional weighted average of post-announcement prices. So this piece is basically what we call the announcement SDF. So the result basically boils down to what announcement premium tell us about these partial derivatives. So here's kind of a more kind of mathematical intuition of the model, which is in the full theorem, we're going to assume continuous probability space. Why? Because I want to say something really precise about preferences. I want to have information on asset prices on a rich enough set of assets, so so they can put restrictions on the preferences. If I assume continuous probability space that allow me to construct a set of very rich assets, I can ask people's attitude. I can ask people's, I can use that allow me to use asset prices to back out preferences. The finite state example that I give you is nice, but it's kind of restrictive. It doesn't allow us to prove some of the more general result in our paper. So assume a continuous probability space, assume integrability. The certainty equivalence functional is mapping from the space of random variables, which is your continuation utility, to the reals, right? Let's say it's a mapping from the L2 space of random variables. Therefore, the derivative of the certainty equivalence functional is a locally linear approximation of certainty equivalence functional. In other words, it's a linear functional defined from L2 space to the reals. By the standard representation theorem in functional analysis, it's going to have a representation. That vector of partial derivative is going to have a representation in L2. Our main result relies on the following observation, which is increasing in second-order stochastic dominance. Assuming differentiability is equivalent to the following property of the partial derivatives. So again, partial derivatives is so I'm going to denote this partial derivative. That's going to be a vector of partial derivatives, and that's a random variable. If I pick two states of the world, omega and omega prime. Suppose omega is a high utility state relative to omega prime. This property says the partial derivative evaluated at omega has to be smaller than the partial derivative evaluated at omega prime. That's a defining characteristic of increasing in second-order stochastic dominance. But in the previous page, I also told you that the partial derivatives are probability distortions because they are announcement SDFs. This is exactly what you need for a positive announcement premium. You need the probability distortion to behave in a way that assign a higher weight in bad states of the world and lower weight in good states of the world. And that's a defining characteristic of second-order stochastic dominance. So it's clear at this point where increasing in second-order stochastic dominance or generalized risk sensitivity is a property of non-expected utility. In the paper, we discuss how does this notion of non-expected utility, this property of non-expected utility, relate to other concepts that people have studied for non-expected utility. For example, uncertainty aversion. So we showed that uncertainty aversion is sufficient, but not in general necessary for generalized risk sensitivity. But if you assume that certainty equivalence functional takes certain functional form, which include a lot of non-expected utility has been proposed in the literature, then uncertainty aversion is equivalent to generalized risk sensitivity. If you take the Klebanov framework of smooth ambiguity preference, then uncertainty aversion is equivalent to generalized risk sensitivity. Another interesting notion of decision behavior is preference for early resolution of uncertainty. So we showed that the concavity is a very strong criteria on certainty equivalence functional that implies both preference for early resolution of uncertainty and generalized risk sensitivity. But in general, preference for early resolutions of uncertainty is neither necessary or sufficient for generalized risk sensitivity. If you restrict your attention to the class of Krebs-Polias preferences, preference for early resolution is equivalent to generalized risk sensitivity. The only class of preference that satisfies generalized risk sensitivity and is indifferent toward timing of resolution of uncertainty is a Gilbert-Schmeidler preference. So if you impose generalized risk sensitivity and you impose indifference toward timing of resolution of uncertainty, you recover Gilbert-Schmeidler's preference. In the paper, we also provide sufficient conditions under which preference for early resolution does imply generalized risk sensitivity. So this is kind of property of preferences, but from why should financial economists, why should us care about these generalized risk sensitivity? Well, first of all, generalized risk sensitivity give us announcement premium. Can I finish it? And you have a pre-announcement drift if there's informal communications from Fed officials before the announcement, as documented by the Cheslak paper. In addition, the announcement premium put on some quantitative quantitative disciplines on the cost of asset pricing models that we write. Because here's our announcement asset pricing equation. Typically in the literature when we write asset pricing models with non-expected utility, we don't necessarily think about announcement premium per se, we think about the entire equity premium, and you have asset pricing equations like this. So when you write down non-expected utility, you wish that non-expected utility gives you a more volatile pricing kernel. So that's a requirement that M is pessimistic. It has to assign higher probability in bad states of the world. So what this says is that the class of preferences that give you a more volatile non-expected utility, that give you a more volatile stochastic discount factor relative to the expected utility, is exactly the class of preferences that gives you announcement premium. Therefore, the quantitatively large announcement premium in our model post-discipline is informative about the relative volatility of these two components. The fact that most equity premium is announcement premium tells us most volatility of stochastic discount factor has to come from this probability distortion component, or this nonlinearity of the certainty equivalence functional. It cannot come from expected utility. So the macroeconomists are probably right when they assume low risk aversion, but they're missing the most volatile component of the stochastic discount factor if they work with expected utility. So you can write down some quantitative numbers. For example, take announcement return. You can write a Hansen-Jack-Denton bound on the volatility of the probability distortion component, just because the Sharpe ratios on announcement days are particularly high relative to the rest of the days. You're going to get a tighter bound on the volatility of this probability distortion component compared to the typical Hansen-Jack-Denton bound on the volatility of the entire stochastic discount factor. So again, most volatility of stochastic announcement return says most volatility of stochastic discount factor must come from generalized risk sensitivity. It cannot come from the typical expected utility that we write down. So just kind of summarize the theoretical result. I want to draw an analogy from the standard result in expected utility framework, which is we all know that risk premium, you have a risk premium if and only if the von Neumann-Morgenstern utility function is concave. And we have a result that's kind of very similar, which says you have announcement premium if and only if the certainty equivalence functional is increasing in second order stochastic dominance. Announcement cannot be compensation for risk aversion. It has to be compensation for generalized risk sensitivity. Therefore, announcement premium really is a asset market-based evidence for this particular deviation from non-expected utility. In the paper, we also have a continuous time model. In the interest of the time, I just want to mention two things. So in a continuous time model, we can really model announcement as information revolution that come out as a particular point in time. So what happens in a continuous time model is that I want to point to a couple expressions. If you take an interval, there's no announcement, then the equity premium is going to be proportional to the length of the time, just because it's a Brownian motion model and the volatility and the variance are proportional to time. So if you shrink the time interval, if the time interval goes to 0, the equity premium is going to go to 0. That's not true if you have announcement in between. If you have announcement sandwich in between this time interval, as you shrink the time interval, the equity premium is not going to go to 0. It's going to go to something. You're going to have a non-trivial announcement just instantaneously as the information come out. And finally, if you assume there's communications or information, informal communications from Fed officials, and in this model you're going to get a pre-announcement drift, just because information come out before the pre-scheduled macroeconomic announcement. Okay, so let me just summarize that we believe that asset market, the announcement premium in particular, provide convincing evidence for deviations from expected utility in a way that's important for macro model asset pricing, because this intertemporal error, the way intertemporal, lots of we know from macro and asset pricing depends on this intertemporal Euler equation. And if the non-expected utility component is the most volatile component of the intertemporal Euler equation, that tells us how, that's informative about the set of models that we write down. I'll stop here and thank you very much.